All right, so for today, guys, the big topics, okay, in today's lesson, and these are going to be very important for basically everything in this unit, okay, is energy transfer. Okay, energy transfer, the methods by which energy is transferred, okay, the effects that has on a global system. All right, so we're going to be looking at energy transfers, the methods by which it's transferred, and how that looks on a global scale. Okay, so the big three things here. Okay, what are the three ways that heat can be transferred? This is like 3, 8, or 9. 3 ways. Radiation is one of them. Okay, and that's transfer of energy by waves. Okay, that's what you would feel if you were sitting next to a campfire. Okay, you can feel the heat coming off the campfire. That's radiant energy coming off the campfire. Okay, what else? Conduction is another one. Okay, and that is transfer of energy by particle collision. Okay, particle collision, and it happens in solids. Okay, basically exclusively in solids. Okay. So for conduction, as if we have, like, let's say we put a metal spoon into a pot of boiling soup. Okay, do you want to grab that spoon anytime after that? Why not? You're going to burn yourself, okay? Because the heat will conduct through the metal, through the solid part of the metal, okay, up to the handle. Even though the handle isn't in the soup, only the bottom of it is, okay, the rest of the spoon is going to get hot because the particles that are in the soup, they're going to start to move more rapidly. Okay? They're gaining energy. They're going to start to move more rapidly. They're going to run into each other. As they run into each other, they transfer energy, kinetic thermal energy, okay, from one particle to the next, and that can go, okay, all the way up the handle of the spoon. Now, do all solids conduct heat the same? No. Okay, some things are really good at conducting heat, and other things are not. Okay, things that are not good at conducting heat, okay, would be insulators. That's often why we use a wooden spoon to stir stuff as opposed to a metal spoon. Metals typically conduct heat very well, whereas things that are lighter or more porous, okay, don't. Does that sort of make sense to everybody? Okay, what's the last one? We got radiation, we got conduction. This is how energy is transferred in fluids. It involves currents. You might have this kind of oven. Convection. Okay, and this is transfer through currents and fluids. Okay, so for convection to occur, the particles in whatever the material is have to be able to move around each other. They can't do that in a solid because in a solid the particles are really tight and packed. They can only kind of vibrate back and forth. Okay? They can't move over each other. Right? In a fluid they can. They can move past each other, which is why a fluid can flow, can take the shape of its container, okay? Things like that. Okay? A current can get set up in a fluid. Now a fluid can be a liquid or a gas. Right? So we kind of rely on convection to heat our houses. Okay? When your furnace kicks in, right, and the fan starts to blow, okay, it moves the hot air through the pipes and through your house, and you want that air to circulate. Okay? If that air doesn't circulate, it's not nearly as efficient to heat your house. Okay? Some larger buildings don't use forced air like our houses do. They use radiant heat instead. That may mean they have hot water running through pipes, okay? And the pipes are simply exposed and the heat radiates off of them, kind of like this room. Okay? We don't use air currents or forced air. Okay? We have hot water that runs through pipes. Sometimes you can hear it actually, okay? And they just radiates off. Okay? It's not nearly as efficient as moving the air. Okay? It's relying on the heat to move a different way. Okay? Everyone kind of follow me there? Okay. These three are really, really important because there will be practical application questions asking you about how those three methods of heat transfer are either being used to move energy or are being thwarted, okay, or prevented so that energy cannot be transferred. right? So it could be like a question that would say, you know, design something that could keep food cold on a hot day. Okay, well, if I want to keep food cold on a hot day, I want to prevent the heat from getting into that food by these three methods. Okay, how do I prevent radiation from getting there? Okay. Okay, an insulated container is probably going to prevent these two things. But waves have to be bounced off, or what starts with an R, reflected. Right? If you look at, like, for example, if you have insulated mud, okay, like this one here, the inside of it, okay, is silver. Or silver colored anyway, okay, which is a highly reflective surface. Not as good as white. White is the most reflective color, okay, but it reflects the heat waves from the coffee back in, doesn't allow them to escape. Okay. Also in a, like a really well-insulated, well-designed mug, there's also going to be a vacuum. There's going to be an inner cup where the liquid actually is contained, and then there's the outer covering. In between there is a vacuum. That means there's nothing in it. If there's nothing in it, then there are no particles that can collide with each other to transfer the energy from the inside to the outside. And if there's no particles, there can be no currents set up, okay, allowing energy to transfer from inside out. Now, are there places where that can still happen? Yeah, near the top, that space isn't as big. Like, if I hold the bottom of this cup, it's actually quite cool at the bottom. But if I touch it here near the top, it's warm. Okay? That's where the heat's being lost. Okay? That's where there's less of that stuff that's preventing those three methods of heat transfer. Okay? So some of it gets out there. That sort of makes sense? Okay, so there's a practical application kind of question. We'll talk about a few situations where those things apply today. Okay, so those are the big three. If you didn't write them down, you probably should. Okay, they're the big three. We're going to talk about them quite a bit today. All right, we're also going to look at this kind of structure of the Earth a little bit, three parts of the Earth. By three parts of the Earth, I mean atmosphere, hydrosphere, and lithosphere. That's the liquids, the gases, and the solids. Okay, and look at how energy on Earth is absorbed, used, and reflected. Okay, that's probably the second most important thing. Okay, in today's lesson. Okay, the only source of energy for Earth is the sun. Okay, so all the energy the Earth gets has to be absorbed, okay, from the sun. But it doesn't all get absorbed. Three things can happen to light when it strikes the Earth's surface. It can be absorbed, it can be reflected. The last one's probably trickier. No, that's still absorbed. But yes, sort of. Converted. There's one group of organisms on Earth that can directly use the sun's energy and convert it into chemical energy. They are plants. What process? Photosynthesis. Okay? Those are the three fates. Okay? That's what we call them. Three fates of energy when it reaches the Earth. Okay? The three fates are absorption, reflection, conversion. Right? Conversion is always through photosynthesis. Okay? Now, what kind of things could affect how much energy gets absorbed versus reflected?
Location of the sun in comparison to the Earth.
Okay, location of the sun in comparison to the Earth. We talked about that before, a little bit before Christmas, how the angle of the sun changes throughout the year. Okay, right now we've got some of our lowest angle sunlight coming in. Okay, not a lot of energy coming from it in that regard. What else? What determines how much energy gets reflected versus absorbed? The atmosphere certainly can. Yes, it can certainly affect that. If it's a cloudy day, then a lot of energy gets reflected off the cloud tops because they're what color? White. Okay? White reflects all light. Black absorbs all light. Okay? So if something is very light in color, it's going to reflect a lot of the light away. Kind of like what we see outside right now. Okay? Not only right now are we getting the least intense and least direct amounts of sunlight, but the ground is covered in white stuff. Okay, it's covered in white stuff, and that white stuff is snow, obviously. Okay, and it's reflecting away a lot of the energy. Okay, in the summertime, do we absorb a lot more? Yeah. Okay, absorb and convert because the plants are alive. Okay, and the ground is darker in color. Okay, that making sense? Okay. Now, right now, how many people know what's going on in Australia right now? Okay? Like the whole continent is basically on fire. Okay? I don't know if you've seen any of the kind of recent updates, but they've got these massive wildfires going on. There's basically no place in the country you can go where there's not a fire. Okay? They're really concerned because a lot of ash is ending up in the atmosphere. We know what that's like because we've had times where there's been lots of forest fires and you can barely go outside. It smells like a campfire no matter where you go. There's a lot of ash coming down. You see it in your house. It's like take your finger running across the counter and it's covered in ash. They're concerned about that because they just recently landed some study vehicles, helicopters, things like that, on the glaciers in New Zealand, which is very close to Australia. And the snow on those glaciers is now kind of a light orangish brown, okay, because of all the ash. Right. So what's that doing to that snow now? What's it going to make it do?
Melt faster.
It's going to make it melt faster. Okay, because it's making it darker. It's absorbing more solar energy, and of course, worst case scenario is it's also summer there, so they're getting their long days and direct sunshine and all of that kind of stuff. Okay, they're very worried about flooding. Okay, and massive loss of their freshwater stores because of the glaciers going to be melting a lot more now that they're covered in that. Okay, now obviously that'll correct itself next year. Fresh snow will fall on them and they'll be light again. Okay, but for now, they're very concerned about the amount of energy that will be absorbed by those glaciers and how much ice will melt as a result. All right, some of this stuff making sense. All right. Okay, so the atmosphere. Okay, atmosphere is really important. It plays an incredibly large role in the transfers of energy on Earth. Okay, the absorption of energy on Earth, reflection of energy, all of that kind of stuff. Okay, it is the blanket of gases that surrounds our planet. Okay, this part of the Earth, the atmosphere, is most responsible. I think I said this already. I'm going to say it again because it's that important. Okay, is most responsible for transferring energy from place to place on Earth. No other part of the Earth is as capable of moving energy as the atmosphere because the atmosphere is the most fluid part of the Earth. Okay, it's more fluid than the oceans. It's more fluid certainly than the solid rock. Okay, so it can move very easily. What do we call moving air? Wind. Yeah. Okay. Wind happens in the atmosphere, and wind is an energy transfer mechanism. Essentially, it's a convection current. Okay, it is the result of the second law of thermodynamics. Wind occurs because there's either a difference in energy or a difference in pressure, or both. Okay, both result in air moving, and that's going to transfer energy. Okay, so the atmosphere is the layers of gases that surround the Earth. The innermost layer, and I'm not ever going to ask you about the names of the layers, okay, but the most important layer for us is the troposphere. Okay, that's the layer in which we live. It extends to about 11 kilometers above the surface, okay, and contains gases that support life. The stratosphere is the next layer. It's also pretty important in terms of energy transfers and weather. Okay, it extends to about 50 kilometers. Okay, and then the layers above that are more about, ozone layer, magnetosphere, kind of all of that kind of stuff. They're very thin. You've never survived in them. Okay. But those are the two layers that we're going to be most concerned with. Okay. Obviously, the troposphere is the thickest part of the atmosphere because it's closest to the Earth. Okay. The atmosphere is pulled towards the Earth by gravity, and that's what creates atmospheric pressure. Okay. Those gases have mass, and as a result, they have weight. Okay, and they push on us. That's what we feel as atmospheric pressure. If you've ever gone up in the mountains or down in the mountains or in a plane really quickly, what happens to your ears? They pop, okay? And that's because the amount of pressure, the amount of gas above you has changed rapidly, and so the amount of pressure on one side of your eardrum is different, causes your eardrum to move. It can actually be a bit painful if you're really sensitive to it, okay? And until the pressure balances, when your ears pop, okay, you kind of feel that weird sensation. Okay? It's a difference in pressure. All right. Now, obviously the part we live in, like we said, extends to about 11 kilometers above the surface. Okay? That means there's really only a few places on Earth you can stand where you're not in the troposphere. Okay? That would be like K2 and Everest. Okay? They're about the only two places where you can stand where you're going to be actually in the stratosphere. How long can you stay there? Not very long. Even with supplemental oxygen, you cannot stay there very long. Okay? There's a reason climbers call the area above 25,000 feet the death zone. Okay? Okay? It's called that because you are slowly dying, okay, when you are in that area, and that is simply because the amount of gas, thus the amount of atmospheric pressure, is too low. Okay? And as a result, your body is just not designed for that. Okay? Fluids start to come out of your tissues and into places like your lungs, and that can be very bad. Okay? Your blood doesn't work properly. Obviously, there's very little oxygen there. Even if you have supplemental oxygen, you can only carry so much of it with you. Okay? That can be a problem. Okay? So you cannot stay in that area for very long. Okay? Also, because you're in the stratosphere, you are close to a wind mechanism known as the jet stream. The jet stream is a very important energy transfer mechanism, and it's a very high-speed wind. It's often what blows people off of those mountains. Okay? If it happens to move across the mountain, which it can do very rapidly, okay, it can bring changes in weather very quickly. Okay? All right, so that sort of makes sense. Okay. All right, so the atmosphere, okay, plays a crucial role in maintaining the Earth's temperature, and that has a profound effect on the Earth's climate. Much of the incoming solar radiation is reflected away from the Earth by particles, that's water vapor and ozone, and by the reflectivity, or, and this is a key word, albedo of the Earth's surface. Okay, albedo is the reflectivity of the Earth's surface. Right now, here, our albedo is very high because it's covered, the ground is covered in snow, snow is white, white is highly reflective. In the summertime, the albedo is very low. A lot of energy is being absorbed and converted by plant life or absorbed by simply the ground, the air, lakes, whatever. Okay, all of it is much darker in color, so more of it gets absorbed. So you can see here in this diagram on the right, okay, in the wintertime, okay, we've got solar radiation coming in, okay, and 85 to 90% of the radiation that actually gets through the atmosphere and reaches the Earth's surface is reflected away. 10 to 15% of it actually gets absorbed, and that would mostly be by areas that are treed. Okay, where the trees are, especially if they're evergreen trees and they're kind of dark in the wintertime, they can be absorbed there, or bare outcroppings of rock. Okay, so very little energy being absorbed during that time. Okay, now to take advantage of this idea, this albedo, okay, what do we do on the roads? Well, salt helps to melt the ice on a chemical level. What else do we throw on the roads? Sand. What does the sand do to the snow? It makes it darker. Exactly. It's also good for traction. Okay? Make no mistake, it helps with traction. Okay? But its main purpose is to lower the albedo of the snow. Okay? Combine that with salt, and you get a combination of things that absorbs more energy and lowers the melting point of ice, so that it's melting more effectively. Okay? Keeping the roads more clear for us, that makes it safe. Okay? So that's the whole reason why we do that. Okay. Obviously, in the summertime, okay, we're looking at a much different situation. Up to 70% of the sun's radiation is being absorbed by the ground. Okay, about 10% of it is being reflected off of like water bodies, and about 20% would be reflected off of the Earth's surface. Okay, so a much higher rate of absorption because the albedo is much, much lower, okay, during that time. Okay, so what we have here in the diagram on the left is kind of what happens to the solar radiation when it comes in. Some of it obviously can be reflected by clouds. Clouds are white on the top. Okay, some of it is backscattered by the air. Okay, backscattering is what makes the sky blue. Okay, it is not because the sun reflects off the ocean. Okay, I know somewhere along the way somebody tells you that. Okay, I don't know why, but I often have people say that to me when I ask them, why is the sky blue? Because it reflects off the ocean. The ocean's clear, guys. Okay, water's clear. It's not blue, right? But it looks blue because it reflects the sky. It's actually backwards, right? What makes the sky blue is simply its composition. Okay? So during the day, during most of the parts of the day, okay, sunlight comes in, and it's because of the composition of our atmosphere, the wavelengths of light that are blue get scattered, okay, making the sky blue. Obviously, in the early morning at sunrise and late at night, okay, well, not so late right now, but when the sun sets, the sky is what color? Orange. Okay, orange, red, okay, and it's that way because when the sun is low, it's now passing through parts of the atmosphere that contain particulates. okay, smoke, ash, dust, whatever, okay, those tend to scatter longer wavelengths, like red and orange. Okay? When the forest fires were happening, okay, did you notice the sky had a much different color? Okay, it's got an orangish. Well, there's lots of particulate and ash and things that scatter longer wavelengths, okay, making it look that color as opposed to blue. All right, so we've got that kind of stuff going on within the atmosphere. Some of the atmosphere will absorb, okay, solar radiation, especially if there's a lot of water vapor and other gases. Okay, some of it will obviously get to the Earth's surface and be absorbed there. Some of it will be reflected by the Earth's surface. Okay, and some of that reflected radiation gets all the way back out into space. Okay, some of it will get absorbed on its way back out. Okay, and some of it will actually get reflected back and forth a number of times due to the greenhouse effect. Okay, yeah, the greenhouse effect's a real thing. Okay, and it's actually a good thing. If we didn't have a greenhouse effect, Earth would be very, very cold. Okay, so we do need some greenhouse gases in the atmosphere. Greenhouse gases include water vapor. Okay, water vapor is actually one of the strongest greenhouse gases. Methane would be another one. Okay, carbon dioxide obviously is one that we're very concerned about. Okay, methane, anything. All right. So remember, off of this one, albedo, important term. Will come up over and over. Okay, so gases present in the Earth's atmosphere help to maintain the Earth's temperature and climate. Carbon dioxide, CFCs, methane, ozone, nitrous oxide, okay, they all allow incoming radiation through, but absorb the long wave radiation that would normally escape on their way out. That helps to warm the atmosphere, okay, and thus the planet. Oh, sorry, I put this picture on here, and it has nothing to do with this. I forgot to put it on here. Remember we talked about the rain shadow thing there before Christmas? When water vapor goes, or when warm air masses come off the Pacific, they go up over the mountains, and on one side of the mountains all the snow falls. Okay, this is actually seeing that in action. Okay, this is Mount Robson, which is the highest peak in the Canadian Rockies. Okay, we got this. You'll see what happens if you've ever. Has anyone ever been? It's actually pretty cool to go there. But what you'll see is the mountain will be all clear, and then all of a sudden, a cloud will come out of nowhere. It'll just form around the mountain and obscure it, and then move past. And then the top of it will be covered in fresh snow, and then the sky will be clear again. And what's happening there is the rain shadow effect. A warm, moist air mass approached the mountain and was forced up and over it. And as it got high enough, okay, the water vapor that was in it condensed. Suddenly there's a cloud there, there's some precipitation that falls, goes over the cloud, it's gone. Okay, that's kind of the rain shadow effect. You can kind of see that happening here. Okay, this would be where all the moisture is. You can see that as it passes over, the cloud gets really thin and falls down to the other side. All right, hydrosphere. So the hydrosphere is all the water on Earth in all three states. Okay, vapor, liquid, and ice. Okay, that's the hydrosphere. Okay, so all the water on, above, and under the Earth's surface is known as the hydrosphere. Okay, less than 0.1% of all the water that's evaporated from the surface of the Earth is returned to lakes, rivers, or streams, or seeps into underground hollows. The rest runs to the ocean or is frozen in the polar caps. Okay, so basically what we're saying is, on a hot day in the summertime, when water evaporates out of a puddle here, that water is not coming back here. Okay, it's not going to fall straight back down on the place it evaporated from. The atmosphere is constantly in motion. It is going to move that water somewhere else. Okay, and by the same notion, when we get water here, it didn't evaporate. Here, most likely, it evaporated from somewhere else and moved here. Okay, by convection through the Earth's atmosphere. Okay. All right. Now, the water cycle. How many times have you learned this in your school career? Too many. One more time. Okay, water cycle, okay, is essentially a way that energy can be transferred on Earth. Okay, because it takes a lot of energy to melt ice and evaporate liquid water into a vapor. Okay, both liquid water and water vapor represent large amounts of what we call latent heat. Okay, that is energy that is stored in a material because of its state. So water vapor contains huge amounts of energy, about this much, 2,260 joules per gram. Okay, So if I have water vapor, okay, floating around, every gram of water vapor contains 2,260 joules worth of stored latent energy in it. Okay? That means that when that water vapor goes to another area and condenses back into a liquid, what happens to that energy? It's released. Okay? It's one of the big ways that energy can be transferred from one place to another, especially an equatorial area to a more polar or mid-latitude area. Okay? If a large air mass containing a lot of moisture or water vapor moves from one place to another, it is bringing huge amounts of energy with it. All right, so the main focus of the water cycle for us is that movement of energy. Am I still going to ask you about the parts of the water cycle? Yes, because the parts of the water cycle are where that energy is going to be changed. Okay? So obviously, the input of this energy occurs during evaporation and transpiration. Okay? So evaporation is just solar-driven liquid water changing into water vapor. Okay? Evapotranspiration, or just transpiration, is evaporation of water from the surface of leaves, plants, okay, things like that. Okay, still takes the same amount of energy. So both ways put water vapor into the air and this energy. Okay, when that water vapor condenses, then we get precipitation, either as snow or rain or hail or whatever. Okay, that's going to represent now that energy being returned or transferred to this new place, as well as a new supply of water. Okay? So when that precipitation occurs, okay, essentially once it hits the ground, a couple of things can happen to it. It can run off, okay, which is what typically happens to most of it. Okay, it hits the Earth's surface and just starts running downhill due to gravity, ends up in streams and lakes and things like that. Okay, if it ends up in a lake, we call that freshwater storage. Okay, it's water on the surface of the Earth that's not moving, that's staying put. Okay, it can also be absorbed. If it's absorbed, we call that infiltration. You may or may not have learned that part of the water cycle before. Okay? Infiltration means water percolates through the soil, possibly even through rocks, and into underground storage areas called aquifers. Okay? How many people have a well? Okay. If you have a well, you are tapping an aquifer for your water supply. Okay? Aquifers are typically recharged by rainfall, and sometimes springs are an example of like water coming out of an aquifer. Okay? But typically wetlands and things like that are what are going to recharge an aquifer. Okay? It takes a long time to recharge an aquifer. You can actually overdraft, okay, on aquifers sometimes. If we have a really bad drought, sometimes people's wells will go dry temporarily. Okay, so you have to watch out for that. Okay, but infiltration is the process that recharges those. Okay, so we got infiltration, that's freshwater storage, but it's underground. Okay, freshwater storage above ground is lakes. Okay, and then water storage is the ocean. Okay, obviously there's a lot of water there. Okay, but it's not drinkable. All right, so the processes we're looking at. Okay, evaporation and transpiration. Okay, precipitation, runoff, infiltration, storage. Okay, those are the processes we want to be able to identify. Okay, and the other thing we want to recognize is these two processes represent energy in. This process represents energy out. Okay, that's where that transfer of latent heat or latent energy, okay, is going to happen. Okay. Okay, so most of the Earth's water, 97% of it, is in the oceans, is saline, it is not drinkable. Okay, only a small portion is fresh, and 3/4 of all that fresh water is locked away. Okay, locked away in polar ice caps, glaciers, okay, things like that. Okay, and 1/4 of that 3% is known as groundwater and is found in underground water-bearing forest rock. Now, the thing with aquifers, I don't want you to get this picture in your mind because this happens, of this underground lake. Okay, it is so not a lake. Okay, it's more like if you fill the glass with small rocks. and then poured water into it, you would be drawing the water out from between the rocks. That's what an aquifer looks like. It's more like a saturated kind of rocky area. All right, so like we said, we can have the oceans, okay? We can have lots of runoff of fresh water, but the fresh water all comes from, okay, our glaciers, at least for us. Okay, it comes from melting snow. Now, how fast are those melting? Yeah, they're melting pretty fast, actually, lately. Okay, that's one of the big concerns, is that the size of our glaciers is decreasing, and the glaciers represent source of fresh water for us. They represent habitat, like, well, the water anyway represents habitat for lots of native species like fish and things of that nature. Okay, when I took that picture, that's 2003. Okay, so it's a long time ago. But you can see that that glacier used to be a lot bigger. It used to fill the valley clear up to this rocky ledge up here, and worse than that, at the toe of the glacier, okay, so kind of where it ends, you walk about 2 kilometers, and then there's a little sign, and it says, in 1901, the Alpine Club of Canada marked this spot as the toe of the glacier. So in 100 years, it has receded like almost 2 kilometers. Okay, now that's just length. It also shrunk vertically. Okay, now I'm not saying that's climate change. It's all bad. It's a natural process. Okay, things are going to melt. Things are going to, things are going to change. But certainly the rate at which that happens is a concern. And the more of it that gets exposed, okay, the more rock gets exposed around it. Rock has a low albedo. It warms up. It's going to increase the rate at which the ice melts. All right. Then we got the lithosphere. Okay, the lithosphere is all the solid rocky parts of the Earth. Now, how much of a role in energy transfer do you suppose this part of the Earth has? Not a lot. Okay, energy does not travel through solids very well, very fast, or very far. Okay, so the lithosphere is more about the absorption part. Okay, it's going to be absorbing a lot of the solar energy, but not allowing it to move around. It's great for catching it in one particular place. It's also important because what grows out of it? Plants, and plants are the other way that energy gets converted, okay, from the sun. Right, so that's more its role. It has virtually no energy transfer role. Okay, the atmosphere is the main method of energy transfer. Okay, the hydrosphere is kind of the second most important. You got ocean currents and you got the water cycle. Okay, those are big. Okay, but the lithosphere, very little to do with energy transfer, mostly to do with absorption and providing some place for plants to grow. Okay, so the most important part of the lithosphere is the soil. That's the very top layer of it. Okay, so soil is the topmost layer of the Earth's surface. Okay, it's where plants can grow. It's its own ecosystem. It has biotic and abiotic components. That's living and non-living parts. Okay, now soil can be very different from place to place. Right? You might look at this picture here. You see all these rocks here. You see like a salt flat down there, and you probably don't think soil. That's soil. Okay, anything plants can grow in. There's plants here. Okay, is soil. Okay. It may not always be very deep or very nutrient dense or anything like that, but it's still soil. Okay, so we're going to talk a little bit about soil and its role here. Okay, so soil is typically divided into horizons, okay, or layers. If you ever dug a hole, okay, you know that there's like the topsoil, and then there's like clay underneath, and then there's rocks. Okay, and the further down you go, the more rocks there are, until eventually you hit the bedrock. Okay. So that's what we see here. Okay, so you got this. The topsoil is kind of made of 2 parts. There's the organic part that would contain like dead grass and, let's say humus. Okay, and then you got your topsoil. So that's all kind of mixed together. Okay, so really this top layer is the A horizon. That's what we call it. A horizon is the topsoil. Okay, underneath that is what we have. It's called the B horizon or the subsoil. That's where all the clay is. Okay, and there's always clay under the topsoil. Why does clay always end up underneath the topsoil? Well, it ends up being more dense because it gets packed. But how does the clay end up always underneath? Yeah, it does actually have to do a little bit with water. okay? But it also has to do with the nature of the particles. The topsoil is typically made of larger particles that are loosely packed, okay? Clay particles are very fine. So if you take like topsoil and kind of rub it between your fingers, it's going to feel gritty. If you take dry clay and rub it between your fingers, it feels like flour. Okay? It's very, very fine. The particles are much, much smaller. So what happens is, anytime small particles land on the surface and then it rains, those small particles get washed down in the spaces or through the spaces in between the larger particles of the topsoil. So they collect underneath. And then the weight of the water and topsoil above presses them down into that dense, hard to dig through big clay layer. Okay? Clay, because it has really small particles, holds onto water really well. That's why it takes a long time for it to dry out. Okay, so when you dig down, it seems like it's always moist down there. Okay? And that's because it simply holds that moisture a lot better. Okay? Below the subsoil, okay, and actually sometimes in the subsoil, are going to be chunks of rock. Okay? When you get through that subsoil, you're going to get to the sea horizon, which we often call the parent material, or bedrock. Okay? And we call it parent material because it's what gives rise to the other layers. Okay? This is the layer of rock that is weathered and eroded to form the soil. Okay? That's where soil comes from, the weathering and erosion of rock. Okay? It collects on top and creates soil. Okay, so this would be kind of what you would see if you kind of saw the soil profile around here. Okay, we'd have, you know, a reasonable A horizon or topsoil that has a fair amount of sand in it. Okay, our topsoil typically is pretty sandy because what's our bedrock made out of? Sandstone. Okay, if you've ever dug a hole around here or seen any exposed outcroppings of rock, it's all sandstone around here. Okay, that's why the big rock is such an erratic. Right? It's made of limestone. There isn't any around here. Okay. And then you got the subsoil here. Okay, you got clay in there, and then you got your sandstone bedrock underneath. Okay, so the A horizon is the topsoil. It's a mixture of decomposed rock, living organisms, decaying organic material, okay, etc. So around here in the prairies, we have a fairly thick A horizon because we have a lot of grass, and every year grass goes dormant and then decays and new grass grows each year. Okay, so it creates this thick mat, okay, of humus and things like that, okay, and thatch, okay, that can create that nice thick topsoil, okay, and then underneath that is a typically thin layer of subsoil, and then lots of rock underneath. Okay, so the B horizon has little or no organic matter, because very little living things get down that far, maybe the occasional tree root or something like that. Okay, the rock is less decomposed, so you're going to run into chunks of it. Okay, and there's a high amount of clay, and we talked about why that is. The clay can wash down through the topsoil. Right? So typically in like really tropical places, okay, especially in the rainforest, there's actually very little topsoil. Everything pretty much grows out of the B horizon, and that's because it's constantly being flooded. The B horizon doesn't erode, but the topsoil washes away very quickly. Okay, so typically the tropical rainforest gets its nutrients from the floodwaters, not so much from the soil. It mostly uses the soil to anchor itself, and that's it. All right, and then the C horizon, okay, is our chunks of rock. So you can see actually pretty well here, okay, that there are chunks of bedrock in the subsoil, okay, but the further down you go, those chunks of rock are closer together and they become kind of more solid, okay, and that's our parent material there in the C horizon. Okay, questions there? Everybody good with that? All right. I'm going to give you about a 4-minute break here, just because I've been talking nonstop. So I'm going to give you a little break, and then we're going to talk about energy. Okay, after that. Okay, so when we're looking at the atmosphere, okay, as a mechanism by which energy is transferred, okay, it's going to be using almost entirely convection to move energy around. Okay, now remember, convection is the movement of a fluid. Okay, in this case, the movement of the fluid is the movement of the gases that surround the planet, and we call that wind. Okay, wind is caused by either differences in pressure or differences in energy. Okay? We always want to have a balance, or nature's always trying to achieve a balance. So if there's an area that's hot, there's an area that's cold, energy is going to flow from hot to cold. And when it does that, it moves the medium through which it's traveling, and that's going to be the air. Right? So it's going to cause the air to move. It's going to cause wind. Wind is going to bring transfers of energy. Okay? So when we're looking at conduction, convection, and radiation, like I said, convection's the most important in terms of transferring energy on Earth. In terms of getting the energy to Earth, what's the most important? Radiation. Radiation is the only one of these three heat transfer methods that can work through the vacuum of space. Because both convection and conduction require particles to move. In the vacuum of space, what is there none of? Particles. Okay, so radiation is the transfer of energy by waves from one place to another. So it's getting here by radiation. Okay, when it strikes the Earth, three things can happen. It can be reflected, absorbed, or converted. Okay, and that's what's happening with that radiant energy. When it's absorbed, especially if it's absorbed by the atmosphere, that's going to cause convection to occur. If it's absorbed by the Earth's surface, it's going to cause conduction to occur. Okay, and some of that reflection, okay, that's going to occur is simply radiation going back. Okay, so all three methods are going on all the time, but convection is probably the most important on a global scale. Okay. So does that sort of make sense? Okay, so what we have, okay, with like if you had something like this, okay, we get hot air rising, cool air descends, hot air rises, cool air descends. You're going to see as we talk about wind patterns tomorrow, okay, that's really important in terms of cycling air and moving air from the equator to the more northerly parts of the world. But that's a very simple convection current. Okay, if you've ever been like to the ocean, I don't know if you maybe noticed this or not, but in the morning, the wind usually comes off of the ocean, and at night it usually goes the other way. Okay? And that's due to differences in albedo causing a convection current to occur. So, in the morning, this is the ocean. This part. Okay, and then this is the land over here. That's a tree. Okay. All right. So the land is obviously a lot darker than the ocean. Okay. Land heats up faster than water does for a couple of reasons. It's darker, but it also has a lower heat capacity, which means as it absorbs energy, its temperature changes really fast. Whereas the ocean is lighter and has a much higher heat capacity. That means it can absorb a lot of energy without changing its temperature very much. So what we get is air over the land rises because it heats up more quickly. Okay. Well, if the air only rose and nothing moved in to replace it, we create a vacuum, and everyone would die. Okay, that would be bad. So what we get is cool air comes in off of the ocean, and this starts to cycle. Okay, and we get a very simple convection current. Hot air rises, cool air moves in to replace it, so now that hot air can't fall back down where it came from, so it starts to circulate in a simple convection current known as a sea breeze. Okay. At night, the opposite occurs. The ocean, which has had all day to absorb sunlight, has absorbed a lot of it, but it holds that energy better than the land does. So the land cools off faster. And now, air above the ocean starts to rise, air from the land rushes out to replace it, and you get what's called the land breeze. It's actually working in reverse. It's still a convection current, okay, but it's always caused by these differences in energy. Okay? That happens on a global scale as well, and we're going to look at that not today but probably tomorrow. So that's convection. Okay, obviously conduction, okay, is what would happen if I had a solid object and I was heating one end. Okay, the particles would move very, very fast here where the heat source is. Okay, and as they move, they run into each other and they cause particles to move through the entire thing. Okay, bumping into each other. It's kind of like, has anyone ever been in a mosh pit? Seen a mosh pit? Okay, so in a mosh pit, everybody's like all cramped in there, right? And you can't really move around, so you're just like, you're bouncing around and moving, and people are running into you. But it's really hard to get in or out of it, okay? So people can transfer their energy to each other. Okay? You run into somebody, they stumble a little bit, the person beside them stumbles a little bit, but eventually it kind of dissipates. Okay? That's kind of like what conduction is. Now, also similar to that, okay, is like the crowd surfing that can occur. Okay? When a single person in the mosh pit acquires more energy than everyone else, i.e. they're lifted, okay, they're able to flow over the solid part underneath. Okay? It's like they've changed state from solid to liquid. They're now able to flow. Their particles are farther apart. There's never as many crowd surfers as there are people in the mosh pit. Okay? There can only be a few of them because they're going to be more spread out because they have more energy. They require the energy for the rest to stay up there. Okay? Now, there's no like analogy that goes further to show them evaporating because that would mean they would vaporize. Okay? Get the idea. Yes. All right. So, water condensing in the atmosphere releases this thing we've talked about already called latent heat. Okay? Latent heat is a really important concept. That's the energy that is stored or possessed by a material due to its state. Okay? Solids have no latent heat. Okay? They cannot change into something else and release energy. Okay? They're the lowest kind of form. Right? But a solid, if it absorbs enough energy, will change state and turn into a liquid. Okay? If that liquid cools enough, then it'll turn back into a solid. And when it does, it releases its latent heat. Okay? And the same thing goes for a gas. Okay? When a gas or when a liquid evaporates into a gas, we have to put a lot of energy into it to do that. And then when it comes back, okay, it condenses back into a liquid, it releases all of the energy it absorbed to become a gas. Okay? So that's latent heat, is the energy you have due to your state. Okay? The higher energy the state, the more latent heat something has.
And latent heat is like only a certain amount, a certain kind of particle can absorb that?
Yes, it's particular to each material. We're entirely going to deal with water. Okay, so like I said before, to evaporate 1 gram of water, which is 1 milliliter of water, is 2,260 joules for every gram. Okay, and that's if it's already at 100 degrees. Okay? So it takes a lot of energy to heat water and evaporate it, turn it into. Okay? And that's actually why, because I'm sure you've all had this experience, you're having a nice warm shower, then you get out of the shower, and almost immediately, as you're trying to dry off, you start to feel cold. Okay? Same way sweat works. Okay? When you sweat, the sweat starts to evaporate. Where is it getting the energy from to do that? From you. Okay? That's why sweat cools you. Okay? It steals this much energy from your body in order to evaporate. Okay? So if you can get a few grams of sweat to evaporate off of your body, okay, it's going to take a lot of energy away from you and make you feel cooler. Same as when you get out of the shower, you're wet. Okay? And so as a result, water starts to evaporate. It takes energy from your body to do that. That's why in Canada, we always say if you're going outside and it's cold outside, you should dress in, okay, clothes. Any other word starts with L. Layers. Okay? The worst thing that can happen to you on a cold day is sweat. Okay? If your clothes become sweaty, you'll start, you take off a few layers, and that sweat starts to evaporate. It takes the energy from your body. You can become chilled. Now, if you're continuing to move around, it's not as big a deal. Okay? As long as all the layers don't get wet. If only one layer gets wet, you throw dry layers on top, or you take that layer off, put dry layers back on. Okay? You can stay warm that way. But as soon as you're sweaty, and you stop the activity that was making you sweaty, you're going to get chilled very quickly. And it's due to this. It's due to latent heat. It's due to the amount of energy that is required to get rid of that moisture. Okay? All right, so latent heat is going to be a really important energy transfer mechanism. Okay? Moving moist air around on the Earth is going to move a lot of energy around. Okay? So the processes are obviously going from a solid to a liquid, it's melting. Going from a liquid to a gas is evaporation. Going from a gas to a liquid is condensation. Going from a liquid to a solid is freezing. If you go directly from solid to gas, that's sublimation. It's pretty rare. Carbon dioxide. Have you ever seen dry ice? And it's what they use in like a smoke machine. Okay. when you have solid carbon dioxide, okay, dry ice, we call it dry ice because it's not water ice, it's carbon dioxide ice, okay, it will go straight from solid to gas. It will not go through a liquid phase. It goes straight from solid to gas. Okay? Sometimes when you get certain types of like you order certain types of frozen food, they'll be packed in dry ice. Okay? It lasts longer and obviously doesn't get wet, okay, because it evaporates. Okay? So you can have that process, or you can go to something called deposition. That's straight from vapor to ice. We see that actually. Okay? We had really nice examples. It lasted a long time. Whenever we get a hoarfrost, okay, and we get that the trees are all white, you get a thick layer of kind of frost and ice on them. Okay, that's deposition. Water vapor has gone directly from vapor to solid. Okay, that's kind of what's going on there. Okay. Now, lithospheric transfers, okay, like we said, for the lithosphere, basically everything is by conduction. Okay, we're going to get only energy being transferred by particle collision in a solid. They can't flow. There's no convection. There's no radiation, okay, in there. Okay, and then obviously plants can convert the radiant energy directly, okay, into chemical energy. Okay, so we've gone over these things now a bunch of times. 3 things that can happen to the Earth's light when it strikes the surface: absorbed, reflected, and how much is absorbed or reflected is based on, starts with A, albedo, okay? Or it can be converted by plants using photosynthesis, okay? The 3 ways that energy gets transferred once it's here: radiation, convection, conduction. Okay? So remember, you're going to get some sort of practical application type of problem here that's going to say, hey, here's a structure, or here's something, here's a situation, we want to either make energy transfers work for us, or we want to thwart them, we want to stop them, okay, things like that. So here's another example. How many people have ever built a quinsy? Okay, really? Okay, so here's what a quinsy is. A quinsy is like an emergency snow shelter, basically. Okay, you shovel snow into a big pile, and then you hollow it out and crawl inside. Okay? It's not packed. Okay? Like if you pack the snow, it doesn't work. Okay? You just throw the snow into a big pile and then you hollow it out. Okay? When you hollow it out, okay, you're leaving essentially a layer of snow between you and the outside world. Okay? That's going to keep you very warm. In fact, you can get the temperature inside a quinsy above 0. Okay? The inside of it will actually start to melt a little bit. Okay? But you can stay very warm even on an exceptionally cold day. Why? Okay, partly, yeah. Okay, you certainly got the inside of the quinsy being white in color. It's going to reflect your radiant energy back at you. That's a good thing. What else is snow? It's an insulator. It's an insulator. That's why animals dig underneath it. Okay, snow is an insulator as long as it's not packed. Okay, as soon as you pack it, what do you force out of it? Air. Okay? Yeah, air, well, when you trap air, when air can't move, it can insulate. Okay? That's what fiberglass insulation in your house does. Some people have seen that, the stuff that's in your walls. It's white or pink. Okay? It's essentially just thousands and thousands of glass fibers, and they all intertwine. Okay? Like this. And trapped in between those fibers are pockets of air. Since that air can't move, convection cannot occur. Convection requires the air to circulate. So if I can trap the air and prevent it from moving, okay, so if this is like an inside wall and this is an outside wall, okay, if that wall is insulated, the heat that's here cannot get out to here because the air cannot circulate. Okay, what would happen if this was not insulated? So if I just had a hollow wall, okay, filled with air, this is the hot side, this is cold, okay, the air against, like in this pocket here, okay, would rise, okay, and then air that's next to the cold wall would move in to replace it. I get a convection current happening inside the wall, okay, and I'm going to bleed energy out of the wall like crazy, okay, I don't want that. If I insulate the wall, the air can't move, okay, and can conduction occur through the air? No, conduction only occurs through solids. Try this sometime. When it's really, really cold outside, run your hand along the wall. you'll be able to tell where the studs in the wall are. Because it'll be warm, and then you feel a cold spot. Cold spot's where the stud is, because the stud goes from the inside of the wall to the outside of the wall. It's the frame of the house. Okay, so it's a piece of wood that's actually touching the inside and the outside. If you ever look at like somebody's, if they do like a infrared camera of your walls, they can see the studs. It's a really cold day, the studs show right through because they're cold. The rest of the wall isn't. Okay? So that's how insulation works. Snow works the same way because snowflakes have irregular shapes, and when they fall together and aren't packed, they trap air in between them. So they act as a really good insulator. Okay? I used to do this when I taught in Lloydminster. We had a snow ecology unit in biology, and I would take the kids out on the coldest day of the year, and I always waited. It was like minus 40, and we'd take them outside with shovels to the football field. You would be surprised how fast people can pile snow when they're cold. Okay? So we make these big piles of snow, and we hollow them out and get everybody inside. And we'd have like 10 or 11 people inside one of these things. Okay? And people would just be peeling off their jackets because it'd be so hot inside. Okay? We'd minus 40 outside. We just put a piece of cardboard over the door, and it would get to like 8, 10 degrees. It would just be dripping. Okay, because it would get so warm inside because we're keeping the radiant energy in, we're preventing conduction, we're preventing convection, all the heat just gets trapped in there. Okay, it acts as a really good insulator. Right, so that could be like a practical application type thing.
Is there a roof on those things, or is it just?
Well, no, it's so you just make a big dome, right, and then you crawl inside, you start hollowing the dome out. Right? Yeah. If you ever do that though, to avoid lawsuits, okay, once you're done making the snow shelter, collapse it. Because if a kid crawls in there and it collapses on them, you're liable. Okay? So if you ever make a Quincy, don't leave it. Okay? Crush it. What we would do is just put the big kid on the top and they can jump until they fell through. And then we could break it up after. Okay? When you're building it though, you also have to be careful not to cut all the way through. Okay? You kind of have to have an idea of your depth. And the best way to do that is to put sticks in. Okay, so once you've made the pile, put sticks in so they go in about this far. If you hit one of the sticks, don't dig in first. Okay? I built a lot of them. You guys should try it. We're not going to have to. And the snow right now is terrible for that because it's all melted. It has to be like fluffy. Okay, so is that stuff making sense? I've done a lot faster than I thought we were going to. Okay, so let's think about a couple other application type things here. Let's say I'm in California. It's really hot. Okay, and I want to come up with a good way to air condition a place. Where do I want the air to come from? From the roof. Why do I want it to come from the roof? Cold air descends. Yeah, so my air conditioning unit on the roof. So I can take advantage of convection. As that cold air descends, what's it going to do to the hot air? Push it up, right? It's going to make it go towards my air conditioning unit. Okay, I want to keep that up there, right? Now, in Canada, even if you have air conditioning, it just runs through the same vents as your furnace. You don't have a separate vents for your air conditioning. If you did, they would be the roof. Okay, they would work a lot better. But typically for us, at least on the main floors of our houses, okay, our vents are on the floor, and that's because most of the time they're heat. Okay, and so we want that hot air to encounter the coldest air that's on the floor, and then you typically have those grates that are on your walls. Have you ever seen those? Okay, those are your cold air returns. Okay, as air is blown, hot air is blown out the registers, it's actually pulled back in towards the furnace through those. You want those on the floor as well, because that's what the cold air is. That goes back to the furnace, okay, to be heated and recirculated and things like that. Okay, so you've got those running through your house. There's reasons for all of that. Now, does that work as well in your basement? Well, where are the vents in your basement? They're in the ceiling. Okay, you can't run the vents in the floor. Okay, so yeah, in the basement, your heating system doesn't work nearly as well because the vents that are bringing all that are blowing all the hot air, unless you have slab heating, unless you have pipes that run through your floor. Okay, and is that using what kind of energy transfer is that using?
That's using convection.
A little bit of radiation, a little bit of conduction. Yeah, it's heating the entire slab. okay, and then that energy is kind of radiating out of the slab, and that'll cause the air to start moving above it. Okay, it's not as efficient, but it's certainly nice on your feet.
Our entire basement needed just no pipes, nothing, just water pipes.
Yeah, just water pipes. Even electric pipes.
Like, is it like
Like really, like you don't have gas. Oh, but you do for the rest of it. Yeah, okay, that happens sometimes. Yeah. Yeah. Some people like it really, like take it. Okay, so questions on this stuff here, guys? Okay, so couple of reminders here, things to think about over the next couple of weeks. Okay, I'm going to try and find a time that will work during exam week where I have this room and where there aren't too many grade 10 exams going on, okay, and have a help session that you guys can come to, okay? I don't know if that's going to work at all because the exam schedule is not really set up for that anymore. If you're going to want help during exam week, okay, you need to email me and say, Mr. Coderre, I'd like to come in at this time. If I'm available, then I will email you back and tell you where to meet. Okay? It may or may not be in this room. If there's an exam going on in here, then obviously you can't be in here. It might have to be in the lab, okay, or something like that. If you need help, though, I'm available. You just have to email me and let me know when you're coming in. As long as I'm not supervising an exam, then I can help you out. Right? But you do have to just send me an email if you're going to be looking for help during exam week. Okay? Prior to exam week, obviously you got scheduled help, lunch hours, okay, all of that kind of stuff, where you can come in and see me and get your questions answered. I will put the final exam review and the unit exam review up on Google Classroom here either today or tomorrow. Okay, so you can start having a look at those. Okay. The unit exam review at this point is going to be pretty useless because we've only had like 2 lessons. Okay, so there's not going to be much you can do with that yet, but we're going to go over some more stuff tomorrow. Tomorrow we'll go over global wind patterns, that's with convection currents, and specific heat capacity. And the next day we'll go over latent heat, and then we'll talk about biomes, and then we're done. Okay, so that should mean we should finish either Friday or Monday. Probably about halfway through class on Monday is realistically when we'll finish. Okay, we'll do a unit exam review on Tuesday, and you'll have your unit exam on Wednesday. Okay, it's just been up on the board since yesterday. So make note of all that stuff, guys. That's kind of the timeline for right now. Remember that your climatogram activity, okay, that's due on January 9th. Okay, so that's coming up as well. Yeah, you need to make sure you get that done. Okay, recommendations for your final exams. This is your first round of high school final exams. It's very different than junior high. Okay, so you guys have my exam in the afternoon. Okay, so 1 o'clock. So the way that's going to work, okay, is at about 12:45, you'll be allowed into the exam writing area for you guys in this class. Okay. When you come in, okay, make sure that you have all the materials you need for my final exam. That is something to write with. I would say a couple of pencils, a couple of pens, and your calculator, which I will come around and clear. Okay, or I'll have you clear them and leave them clear. Okay, so if you have any programs or anything like that stored on your calculator that you want to keep, make sure you have offloaded them before your exams start, because in all of your math and all of your science exams, we will clear your calculator prior to the exam. And we'll focus everything on it. Okay, it'll be clean slate. So be aware of that. So you'll need your calculator and you'll need something to write with, and that's it. That's the bare minimum of things you need to bring with you to my test. Okay, you're going to get a periodic table, you're going to get a fresh formula sheet, all that stuff will be provided. Okay, you don't even need a ruler. Okay? Just something to write with in your calculator is all you need to bring. Make sure that you do not bring your phone or smartwatch or anything like that into the exam. Okay, any device that can communicate via Bluetooth or Wi-Fi is not allowed in the exam writing area. Okay, so you cannot have those things. Leave them in your locker, please. Okay. The other things that you might want to bring to the test, okay, bring some water or juice or whatever it is you prefer to drink, okay, for the exam, bring that, okay, maybe a snack, okay, granola bar, piece of fruits, apples are really good, okay, bananas are also a pretty good one, okay, stuff that's not going to make your fingers sticky, okay, stuff like that. Yeah, don't bring spaghetti. Okay? Yeah, just you don't need a 4-course meal during your exam. But sometimes if you feel your blood sugar dropping, it's a good idea to have something, just a quick snack. Okay. But remember, it's got to be something that's not going to disturb other people. If you bring something really smelly, that's going to disturb other people. If you bring a 500-gram bag of Doritos, that's really noisy. People are going to get annoyed with you. Okay? So keep that kind of stuff in mind. Something to drink, a quick snack or something like that is also okay to have with you. But don't bring excessive amounts of stuff with you. You're not allowed to even bring in a backpack or anything like that. Okay? You have to just bring in what you need for the test. And that's just because, well, people cheat, and so we have to take all the precautions that we can possibly take. Okay? So just be aware of that. You have, for the exam, 2 hours. And that's it. Okay? Unless you have an allocation through learning support to have more time, you have 2 hours to write the test. You'll know if you know already if you're a person who has that. Okay? So you have 2 hours to write the test. And this is not one of those 2 hours plus an extra half hour. No, that's a 2.5-hour exam. This is a 2-hour exam. You have 2 hours to write it. Okay? Realistically, it should take you about 1 hour and 40 minutes to write. And then you'll have some time to look it over afterwards. Okay? Now, you must stay in the exam writing area for a minimum of 1 hour. Spoiler alert. If you're done my test in less than 1 hour, you didn't do very well. Okay? A challenge. That's not a challenge. Okay? Somebody always asks that when I say that. It is not a challenge. Okay? People who accept that as a challenge really regret it later. Okay? It's not a challenge. Okay? I have only had one student in 20-some years of teaching, okay, that has taken that as a challenge and actually pulled it off. He was brilliant. Okay? He was probably done after 40 minutes. But okay, yeah, he was just one of those exceptionally brilliant people who will probably land on the moon. Okay? Yeah, so don't take that as a challenge. I'm just saying, if you're done after 1 hour, you probably missed something. Maybe many somethings. Okay? Yeah. Oh yeah. You laugh. That's one of the things that people think. There was a written response section, Mr. Coder? Yeah. I only said that every day for 2 weeks before the exam. By the way, your final exam is just like a unit exam. It has a multiple choice section and a written response section. Make sure you do both. Okay? The written response section is worth way more marks. Right now, there are 50 multiple choice, and there are 14 written. Something like that. Yeah. 130.
No, the more marks, the better. It's like the more chance of